All right, picking up where I left off, first thing to notice is that I had a slight mistake because it should have been lambda observed over lambda at the source was square root of this thing. So let's think about that for a second. Lambda observed over lambda source equals square root of 1 minus r sub s over r. Now that should be, I think, compared and contrasted with a result that we have from earlier, del tau del t equals square root of 1 minus r sub s over r. And actually, you know what? This is rather amazing because I think this is a question that I have been asking for, probably the last 5 years, and I think I just worked it out. The trouble is, it's not the answer that most people actually promote. So it has to do with the idea that, well, let me start at the beginning. Let me describe the description that I've always been confused by. Here's what I thought the claim was. Okay, first of all, we're going to look at this term, which I thought made sense. This is basically reflective of the speed of time. That's the speed of clocks versus the speed of time. And I thought of this as a measure of rulers versus the measure of space. And I thought that the explanation for why we needed this was to keep c constant locally. But now I'm thinking it's a different description. That's not quite exactly it. The reason for doing it is to make lambda observed over lambda source equals, let's call it delta S delta R with t equals constant, t theta and phi equals constant, delta R with t theta phi constant. And we're going to make that equal to the period observed, other way around, period source over period observed, which is a delta tau with, delta tau delta t with, with r theta phi constant and r theta phi constant. So to keep our notation more consistent, actually I could just write that once because it's the same thing. So on this side, delta S delta R with t theta phi constant, delta tau delta t with r theta phi constant. So here we're talking about the measure of the rulers. Here we're talking about the time on the clocks. We're talking about the measure of the clocks as time is held constant. We're talking about I'm sorry, what am I saying? We're talking about the measure of the rulers. We're talking about the measure of the rulers while the time is held constant. And we're talking about the time on the clocks where the radius is held constant, where the position is constant. And we're comparing both of these to a Euclidean coordinate, delta r, and, well, maybe either a Euclidean or Minkowski. So you can think of this coordinate as either um, the coordinate system of a distant observer. Um, well, this one is basically the time on the clock of a distant observer. This one is a little bit trickier because it exists in the same space. Because that delta r is the Euclidean coordinate system that basically overlaps. Well, the delta s isn't really a coordinate, it's a measure of a ruler in that space, or it's a measure, actually, it's a measure of a wavelength in that space. It's not a measure of a ruler. So the question here is basically whether the measure of the ruler actually adjusts itself to the measure of the wavelength at the source, or does the measure of the local ruler actually reflect the measure of that wavelength at the source? You know what? Let's get a an idea of exactly what proportion we're looking for here. The exact proportion we're looking for here is 1 minus gm 1 minus 2 gm over rc squared. So I just plugged this into Mathematica, and the difference comes out to be 1 minus 6.9 times 10 to the negative 10th. So the factor that we're talking about there, the wavelength that we should detect, if we are looking at the wavelength of a photon and measuring it with a ruler, um, if the rulers don't shrink with the wavelength, if the wavelength shrinks differently than the ruler, then we would have a factor of 6.9 times 10 to the negative 10th. But there's another thing that comes into play here, because the rulers themselves are going to be compressed according to something else, because just a ruler is made of atoms, and the atoms are going to settle uh, in there. So it might be that let's look at the bulk. Let's compare that to the bulk modulus of the ruler. I'm sorry, Young's modulus of the ruler in a gravitational field. Let's see, for steel, let's say we've got a steel ruler. Steel ruler has a Young's modulus of 200 gigapascals. Let's see, just need to get the formula for Young's modulus from Wikipedia. Here it is. Okay, there's versions of this. Trouble is, we got it's kind of a situation where we don't have a weight on the top, so I can't just take that mass times gravitational field. It's sort of a density equation, so I think maybe might be the form that we want. As a matter of fact, the very bottom of the meter stick is going to compress by a different amount than the top of the meter stick. The very top of the meter stick would have essentially no force on it except for the force of the atmosphere on it. The bottom of the meter stick is going to have the whole weight of the meter stick on it. Still, I just want to plug in some numbers. So 200 times 10 to the ninth pascals over here on the right. Force times, well, force over area. Let's use this form. Force over area is going to be the pressure. Let's use atmospheric pressure, which, if I remember right, is 103,100 pascals. Divided by delta L over L sub naught. And what I'm going to plug in there, oh, I'm not going to plug in anything there. What I'm going to do is compare that to the value that we had up here, which was 6.9 times 10 to the negative 10th. So I'm going to find out what delta L over L is and compare it to, what was it again? Shoot. 6.9 times 10 to the negative 10th. 6.9 times 10 to the negative 10th. And see just how much this part of the steel ruler compresses, and see if it's on the order of that. So in essence, I'm going to take 103,100 divided by 200 times 10 to the ninth, and I think delta L over L sub naught on the order of 10 to the, what is that, 10 to the 6th over 10, actually comes out to be 515 times 10 to the negative ninth, which is considerably greater than this number, which is 0.690 times 10 to the negative ninth. So this number uh, is, a, is about 3 orders of magnitude greater. So we're looking at a ruler, just this top part of the ruler that is only being compressed by the atmospheric pressure. It gets steadily worse as you go down. But this order of magnitude here, 515 times 10 to the negative ninth, that's how much you would expect the top of a steel rod to compress under atmospheric pressure. This is the amount by which it would mismeasure the speed of a photon, or the wavelength of a photon, if that photon was, if the ruler maintained a perfect length, if it wasn't compressed by Young's modulus. So this number is very, very, very small compared to this number, and it's probably something that we would not be aware of if it was a difference. So basically on this matter, we could probably say that this hasn't been experimentally confirmed. I'm going to divide this into cases. Case 1 is the case that I actually think is true, that the ruler could measure the difference in wavelength in principle, but it's just a very, very small thing. And there's other phenomena that affect the length of the ruler even far more than the wavelength of the light is affected. Or case 2. So case 2 is that space actually contracts, so the ruler is contracted by the same factor as the photon. So there's a kind of a big difference in this, because in this case, differences in speed of light would be undetectable. In this version, though, the differences in the speed of light would be very hard to detect. Because we simply don't, because the phenomenon that affects because in this case, the phenomenon that affects just the size of the ruler is just orders of magnitude greater than the phenomena that affects the wavelength of the light. But in principle, if you could really take into account all of the, if you could really, I mean, if you could eliminate for that huge 4 orders of magnitude greater problem, then you could maybe possibly detect differences in the speed of light. But in this case too, there is no possibility of even doing that, because not only is it difficult to observe, it is impossible to observe because the space-time conspires in such a way that the ruler contracts by the same factor as the photon's wavelength. It would really be neat if I could find a way to express these two things in a rigorous mathematical way. The trouble is, I don't think there is anything that I have done so far that allows case 2 to be described, because case 2 requires us to define another space than the variables that we've already got. We don't actually have a variable representing this space where the contraction of the ruler is undetectable. We do have all of the variables for case 1. For case 1, all of the variables are already here. because really what we need to adjust is where I said measure of ruler, measure the ruler measure of the photon's wavelength. This is what this is, measure of the rulers of a photon's wavelength versus the measure of the space. And this is a perfect ruler, the perfect ruler without any Young's modulus. Perfect ruler. And when I say the measure of space, it's the measure of perfect ruler. And that is what's going on here, is that this thing is comparing two different measures. It's a measure of the wavelength versus the measure of the ruler. And so we need another way of asking that question, whether the perfect ruler, because we take a perfect ruler out here in space, compare it to a perfect ruler here on a planet, and we're going to move it over there. And generally, if it is an imperfect ruler, then that ruler will be affected by Young's modulus. If it were a perfect ruler, it would not be affected by Young's modulus. Question is, would it be affected by the same phenomenon that contracts the wavelength, or would it not? And let's call that phenomenon Schwarzschild contraction. Schwarzschild, Z-S-C-H-I-L-D, Schwarzschild contraction. And so there's two phenomena that could compress the ruler. One of them is Young's modulus, which will almost definitely affect a ruler as it comes from here to here, especially if the planet has an atmosphere. I guess you could correct for that to a certain extent by putting the ruler in a vacuum, and then there would not be any pressure. There would not be any atmospheric pressure, at least on the very surface of the ruler. And then you could, or you could just correct, and you could correct for Young's modulus a little bit by imagining that the ruler is compressed by its own weight as it comes down. And then once you've accounted for that, what phenomenon is caused by Schwarzschild contraction is like several orders of magnitude smaller than what you would get from Young's modulus. So you'd have to correct for that. And then if Schwarzschild contraction is there, then the wavelength of the photon, the difference in the wavelength of the photon due to the gravitational field would be undetectable. If the Schwarzschild contraction is not there in the ruler, then the difference in the wavelength of the photon due to the Schwarzschild metric would be observable. Well, I've filled up another approximately 20 minutes. Thanks for watching.